Hello, pre-calculus friends. This is Mrs. Steele back in the video production business for our last chapter of the school year. So today we are going to be talking about limits, and limits is an introduction to calculus. And so the best way to introduce what a limit is to look at this example of our friend the frog who is trying to jump to the end of the 4-foot board. Okay, but the rule of the contest is that the frog can only jump half of the distance that's left. So the question is, can the frog win the contest? So if this board is 4 feet long, then obviously on his first jump, he's only allowed to go about halfway, right? So that means that he's going to be at 2 feet. And then he's starting at 2 feet. So for his next jump, he can only jump half of what's left. So that's going to put him at about 3 feet. And then he's going to keep doing this. So if he's at 3 feet and the end of the board is 4 feet, then his next jump is going to be 3.5 feet. And then for his fourth jump, he can only cover half the distance left. So that's going to put him at 3.75 feet. For his fifth jump, he can only cover half the distance left. So that's going to put him at 3.875 feet. His sixth jump will put him at 3.9375 feet. His seventh jump will put him at 3.96875 feet. And his eighth jump will put him at 3.984375. We could keep going on with this forever and ever and ever, but the answer to the question is no. The frog can't win the contest. With each jump, the frog gets closer and closer to his goal, right, which is the end of the board, but he never reaches it. So this is a non-math example of what a limit is, okay? We talk about approaching a value, getting as close to that value as we possibly can, but not reaching that value. That is a limit. So now let's take a look at a math example. So here we have a function, f of x equals x squared plus 1, and we want to know what happens to the values of this function as the variable x approaches 2. Okay? So if we're going to approach 2 from the left-hand side of 2, that means that we're looking at values of 2, or values, that are smaller than 2, but are getting closer and closer and closer to 2. So I'm going to start with 1, and I just used my calculator and I typed these values in. So I'm just going to go ahead and fill in the table. So when x is 1, the value of this function is 2. When x is 1.5, the value of this function is 3.25. When x is 1.8, the value of this function is 4.24. When x is 1.9, the value of this function is 4.61. When x is 1.99, we get 4.9601. And when x is 1.999, so as close as we can get here to 2, well, not as close as we can get, but pretty darn close to 2, but without being 2, we end up with 4.996001. Okay, so now let's do the same thing. But instead of approaching 2 from the left-hand side, we're going to approach 2 from the right-hand side. So we're going to start with numbers that are bigger than 2, and we're going to get closer and closer and closer to 2. So I started with 3. And when you plug 3 into this function, you get 10. Then I went to 2.5. So then the value of the function becomes 7.25. At 2.2, the value of the function becomes 5.84. At 2.01, we get 5.0401. At 2.001, we get 5.004001. And, whoa, 2.00001, we get 5.00004. Okay, so what you can see here from the work that we did on the left-hand side of the 2 and the work that we did on the right-hand side of 2 is that the values of the function get closer to 5 as we pick x values closer to 2 from both sides, okay? And then this graph right here is just kind of to show us what's happening, right? So here's our value, x equals 2, that we're getting closer and closer and closer to. So if we were to graph what we did in our tables here, when x was 1, the value of our function was 2. When x was 1.5, the value of our function was 3.25. When x was 1.8, the value of our function was 4.24. When x was 1.9, we were at 4.9, and so on and so on and so on. So we just get really close. And then on the other side of 2, we saw the same thing happening, right? So what we saw was that it seemed that the values here were closing in on that value of 5 as we got closer to 2 from both sides. So using limit notation, this is how we would write this. We would say the limit, and underneath the LIM, we would put the value that we're approaching. So the limit as x approaches 2 of our function, so our function here would be x squared plus 1. And sometimes if the function is rather big, you'll see people put that like either in a parenthesis or in a bracket. It doesn't really matter. So the limit as x approaches 2 of x squared plus 1 equals 5. Okay? All right. So now let's take a look at the formal definition of the limit of a function. Okay, so up here in the box, we have the limit as x approaches a of our function f of x equals L. This is read, the limit of f of x as x approaches a equals L. What this means to us is that the values of our function, so the values of f of x, get closer to L as we choose values of x that get closer to a but not equal to a. Okay. And remember, you can pick values that approach a from either side, from the left-hand side or from the right-hand side, so you can look at the limit from both sides. And this is the hardest part for people to understand. It doesn't actually matter what x equals at a, okay? This is kind of a big deal. So our next couple of answers here, or excuse me, our next couple of examples are going to sort of illustrate what we're talking about when we say that it doesn't matter what x equals at a, okay? So we've got our 3 different cases. We've got this first case where we have a curve, and we can see that in case 1, that point right here, this point right here is the point a f of a, okay? And a comma f of a exists. And as you can see, that point is on the curve. So we would say that the limit as x approaches a of f of x equals the point L, right? Because that, or equals the value L, because that's what our point is right there. And it's right on the curve. Now here's another example. Here's a case 2, and we see this quite a bit when we're working with limits. And this is where that whole thing that we just circled above about how it doesn't matter what x equals at a. So here we have that same curve, but instead this time you can see that there's a little hole right there in the curve when x is actually a, and then there's like a solid dot below the curve. So that's actually what the function equals when x equals a. So this would be some sort of a piecewise function, right? So a f of a exists this time, but the point is not on the curve, okay? And then in the third example, we've got this same curve again. It looks a lot like our case number 2. We've got that hole in our curve right there where x equals a, but this time we don't even have that solid dot occurring anywhere. Okay, so this time a f of a does not exist anywhere on the graph. But in all 3 of these cases, and this is what you need to understand about limits, in all 3 of these cases, the limit does exist, and the limit is L, okay? So we're going to write something down here that's kind of important. F of x does not need to be defined at A. The limit is still L. As x approaches A. And that's a very important thing to understand. You don't have to have a value on the curve at that x equals A. As long as both sides of the curve are approaching the same point, the limit does exist. For our next example, we want to guess the limit as x approaches 2 of the following function, x minus 2 over x squared minus 4. Now, however you're going to find these values, you have to make sure that when you're doing something with the calculator that you're using parentheses around your numerator and your denominator so you get correct values. But I would actually like to show you a cool feature of the graphing calculators if you do own one. If you don't own one, you don't need one, okay? You can just do what I showed you here with the parentheses, and you can start plugging these values into your calculator and get the values. But I'm going to show you right now the table feature on the calculator and how you can do this rather quickly if you have a TI-84 graphing calculator. So the first thing that I did is I went into the y equals and I entered in the function that we're looking at. Notice I put parentheses around the x minus 2 divided by, and then parentheses around the x squared minus 4. And I cleared everything else out because I only want that function to be in there. Now I am going to go to second level, and then above the graph key here is this blue table. So I'm going to click second level graph, and that's going to take me to the table. And I have the ability to type in any value that I want here for x, and then it will fill out the table for me. So I already put the values that were on the left-hand side of 2, 1.9, 1.99, 1.999, and 1.9999. And these are the y values associated with those. So now I'm going to type in the x values that are greater than 2 so we can fill in the other side of our table. So I'm just going to type or click here 2.1 and hit enter, and then 2.01 and 2.001 and 2.0001. Okay, and now we've got the values for our table, and that was pretty quick and pretty slick. So I've gone ahead and I've just transferred those values from the table on the graphing calculator into my graphs here. And so what we can see is that the limit as x approaches 2 of our function is equal to 0.25, right? As we get closer and closer to 2 on the left-hand side and on the right-hand side, this function is closing in on 0.25. So now we're going to check this graph on the calculator, and we're going to see what we get. So I'm going to pop up my graphing calculator here, and again, I already have this function in my y equals, so I'm going to go ahead and graph the function. And that's what it looks like. Now, if you remember from chapter 2, we did a lot of these type of functions, okay? So these are reciprocal functions, and this one has an x squared in the denominator. So now I'm going to go ahead and I'm going to use the second level calculate feature. So second level, calculate is above the trace key, and I'm going to calculate the value. So here's the graph of my function. Now I'm going to go to second level trace, calculates above that, and I'm going to just hit number 1 for calculate the value. And I'm going to go ahead and I'm going to type in x equals 2 because I want to know what is the value of this function at 2. And look at that. When x is 2, y doesn't equal anything. If we were to zoom in on that, you would see that in the graph. There would be a hole there.